Okay, great. Thanks for the introduction, Peter, and thanks to everyone who's still sticking around at the very end of a long day into dinner time, I'm sure, for many people. So I kind of wanted to take a little bit of a different approach in this talk and talk a little bit about a couple of different projects and ideas, but from a spin of an operational perspective. Some of the things that we are working on at Microsoft and that I've also pursued as research projects. So I'm going to break down into two major segments here for machine learning and weather, just two strategies for the purposes of this talk. One of which is augmenting existing numerical weather prediction and NWP solutions, for example, post-processing. And the other direction is like new models or replacement of NWP models, which we've seen some talk about here as well. Of course, there's some other approaches for machine learning and weather that kind of fall in between these, but just using these as kind of broad categories for what I'm going to talk about. So first, let's start with the augmenting NWP approach. So numerical weather prediction post-processing can generally be considered as a pretty big success in the past. And there's actually been many decades of work on this. Statistical post-processing is pretty much as old as NWP itself, because from the beginning, we realized that the model's representation of grid cells does not correspond to what reality suggests will happen at weather station locations or where people are experiencing weather. So since the 70s, model output statistics, or MOS, have existed, but often used fairly simple algorithms. Therefore, there was an opportunity here for modern machine learning algorithms to step in and improve on this post-processing. And in fact, it's pretty safe to assume that any commercial weather product you see today, the end consumer result is produced by some form of machine learning post-processing. And we do some of that also for Weather by Microsoft Start. And it's important to keep in mind, though, that like building these machine learning tools into operations is not a trivial process. The entire deployment pipelines can end up being quite complex. So while understandably, there's been a lot of attention focused on the model inference component and how to make inference computationally efficient and minimize latency, it's equally important to make sure that a model is continually being updated with the latest data to keep it performing at its peak. So thanks to the work of our engineers and data scientists, we focus not just on inference automation, but also generating new data for training and also for post-mortem analysis of the actual quality of the product. So when designing the operations for a post-processing system here, it's all about automation, not just in inference, but also data extraction, quality control, model training, and model validation. So it's important to keep in mind that ideally you do need to budget for online model training, and the cost of running a model in production is not just the inference cost. Now all this allows us to avoid some common pitfalls, for example, like garbage in, garbage out. It's taken care of by real-time data quality control, and poor model generalization or performance declines over time is solved by having an online and updated model training process. So while this is a problem that's largely solved, I would say, what is next in NWP post-processing? There's been a lot of attention recently, and rightly so, on extreme events, because the key mission of any weather service is to protect life and property, which is really affected by the ability to forecast extreme events, such as droughts, hurricanes, flooding, etc. And in the numerical weather prediction world, some key revolutions in addressing the predictability of extreme events has been ensemble forecasting and data assimilation. So are there machine learning techniques that can utilize what we've already done in Ensemble NWP to further improve forecasts of extreme events. So the example I'm going to look at here is the ENS10 benchmark. So the ENS10 benchmark consists of data from the ECNWF's IA integrated forecast system model hindcast, consisting of 10 ensemble members available for 20 years of training data. And the task in this benchmark is essentially to take these input 10 ensemble members, pass them through some learned model to predict a corrected output distribution to minimize some ensemble scoring, such as the continuous ranked probability score, or CRPS. And specifically for this very targeted benchmark task, we look at 48-hour forecasts of some key variables: geopotential at 500, temperature at 50, 2-meter temperature on a global half-degree grid. So in this project, which is done in collaboration with some colleagues at ECNWF, we've taken a look at some of the past research on ensemble post-processing, and it becomes pretty clear when you're looking for extreme events that many of the techniques which had focused on optimizing just the mean and standard deviation and assuming Gaussian distributions is really not enough. So instead, we looked at the ensemble transformer technique, which was proposed by Tobias Finn in 2021. So this uses transformers, which are the basis of state-of-the-art text and speech recognition models, and instead applies them along the ensemble member dimension to get a member-by-member post-processing approach that corrects each individual input ensemble member based on its interactions with all other members. And one of the very nice properties of this is that it maintains the physical realism of each ensemble member individually. Our specific approach involved in inserting these the transformer operations inside a unit, both for computational efficiency reasons, but also to get the transformers to learn interactions between the ensemble members at multiple different horizontal spatial scales. This is the table of ranking in the performance metrics as presented in the ENS10 benchmark paper, where they have a couple of benchmark methods, including the raw IFS ensemble. And if we insert here our unit transformer, our preliminary metrics show that we are in a decent margin ahead in first place on this benchmark chart for now. Now this result is fresh off the press, so we haven't yet had a chance to compute the other headline metric from this task, which is the extreme event weighted CRPS, but we'll definitely update that when we have it to test performance of extreme events. Now, our approach is not focused just on the 48-hour forecast for specific variables, but we can also expand to further lead times. And also, because the model is agnostic to the number of ensemble members, we can run inference on the full 50-member ensemble despite only training on 10. And so we see here in the continuous probability score and skill score relative to the raw IFS that our models in the red and orange are outperforming the original IFS ensemble and a member-by-member benchmark. So to summarize, our ensemble transformer can run on the full operational IFS ensemble while maintaining some desirable properties. And in terms of thinking about how such a model might be used in operations, there's of course some notable challenges that still need to be solved. One is going to be manipulation and serving of very large data sets. If we go to the highest resolution available from the IFS ensemble, for example, that is a lot of data to pass into a neural network algorithm. And one of the outstanding problems that remains for ensemble forecasting in general, of course, is communicating to the public the risks and uncertainties involved in extreme events and making user-facing products that can actually communicate this effectively. So now on to the second overarching section here, which is new models or replacements. Now, of course, as we've seen from Karthik's talk, and we've seen over the last couple of years, there's a growing library of work on using advanced deep learning algorithms as surrogates for NWP models and making forecasts that are completely free of physics. Everything from the weather bench, which kind of established an easy to use benchmark data set for this problem, to some of the work I've been involved in, pushing these surrogate models all the way out to sub-seasonal timescales and getting decent performance in a ensemble metrics compared to ECNWF, to, of course, the NVIDIA's ForecastNet, which is getting closer and closer to the performance of IFS for medium range weather forecasting at comparable resolution. So, you know, why is it such an interesting problem to replace NWP? Well, I mean, the arguments basically boil down to efficiency again, and even more efficiency. Seriously though, like NVIDIA's results have shown their model is about 80,000 times faster on a per compute node basis and 10,000 times more energy efficient than a comparable ECNWF IFS solution, which enables a lot of really interesting things, such as very large ensemble forecasts for extreme events, and also reproducing data in near real time, as Karthik was mentioning, using checkpoints and being able to run the model very quickly to resume from checkpoints. Now, Karthik might not put everybody at ECNWF out of their job just yet, but he did definitely make this slide obsolete with some of his most recent developments, talking about adding adversarial loss. And but I did want to mention that these models still do need a little bit more physical realism and some concrete evidence of picking up extreme events better than numerical weather prediction models currently do, in order to really show promise. But then again, this work is actively ongoing and very promising. Now, on a slightly different note in this section is we've seen the use of machine learning to tackle new or perhaps slightly different angle on problems. And one example of this is precipitation nowcasting. So traditional NWP has a few disadvantages for real-time short-term precipitation forecasting, most notably of which is the latency between the assimilation of the latest radar information all the way to the output of forecast fields, even for short lead times. But on top of that, NWP is actually not as accurate as even a simple statistical method such as optical flow because of all the physics involved necessary to convert, you know, between radar information and physical variables. So since these statistical methods are doing so well on short-term timescales, and there's lots of algorithms in deep learning to do things such as video generation or video processing, there's a ripe opportunity here for advanced machine learning techniques to improve short-term precipitation nowcasting. And this isn't new. In fact, it's been around for quite a while now, since the original convolutional LSTM architecture in 2015. But recent developments have really boosted this field a lot. The Google's MetNet2 was able to integrate with NWP to form a more hybrid approach and forecast for longer than just the 1 hour or 2 hours that most prior research had looked at. And in particular, the DeepMind and UK Met Office paper using generative models for radar also had the human component here, where they asked their forecast to be evaluated by expert meteorologists who chose the GAN model's output 89% of the time over competing statistical methods for short-term precipitation forecasting. So at Microsoft, we've been continuously developing and improving our nowcasting product for the last couple of years that is available to users worldwide. We've been using a convolutional LSTM style generator architecture and also added adversarial loss using discriminators inspired by the DGMR paper from DeepMind and UK Met Office. And we also include some conditioning layers to add the short-term HER forecast, her regional model over the US, to improve performance at longer lead times beyond just the short statistical dependencies. And we've used several techniques such as channel stacking, diluted convolutions to reduce the memory and computation footprint of a model to make it more operationally feasible. And in terms of observations, this figure shows the sort of pipeline that the model uses. In the United States region, the latest radar images from MRMS are retrieved with about a 2-minute latency on average. And the inference of the model itself runs in less than 2 minutes. And then there's another 2 minutes approximately for generation of the user-facing end products and text summaries and maps. So end to end, it's about 6 minutes since the data observation time that users can see their short-term forecasts. And the inference itself is controlled by a streaming pipeline based on a message queuing framework, so that it's not bound by the performance of any single component. This was important to use all of the engineering tricks at our disposal, because for precipitation nowcasting, time is of the very essence. So the production pipeline needs to be able to run as efficiently as possible. Finally, we also tiled the CONUS region into sectors with some small overlap that are then blended to enable further parallelization. So with that, I just want to leave a couple of concluding thoughts from some of my experience in a number of these projects and bringing them to operations at Microsoft. First, when designing an operational machine learning-based weather solution, it's important to always keep the end user in mind. So you need to make sure that the model has automation to continuously improve. And for nowcasting, speed is vital. And I didn't really touch on this too much, but it's also obviously very important to have real-time detection of issues. For example, in observation quality control or forecast quality control for post-processing, or problems in the data flow rear their ugly heads a lot in terms of nowcasting. And there's a lot of very promising and exciting research going on in ensemble post-processing and model replacement. But it's important to keep in mind that for operationalizing this in the future, we'll also need products that can effectively communicate to the end users what they can get out of this model and perhaps its limitations and uncertainties as well. And so with that, hopefully I have some time for questions. Thanks.